Today on Hagam Unite, we are going to be tackling the widely held theory of the evolution of the universe, the Big Bang Theory. Specifically, the elements involved in the formation of our universe. Well, at least, try to make sense of it. So what do you think of this topic?
I think it's
Really what?
pretty difficult to understand.
That is true. Making the script for this was a little headache inducing, but you know what? That also means it's mind blowing.
All right then, let's get right into it. Start it off with a bang.
Nearly 14 billion years ago, there was a massive energetic explosion that made the universe expand from a hot and dense state and for it to evolve into the universe that it is now. We look back to when the universe was but a fraction of a second old, back when the temperatures were so high, atomic nuclei couldn't even form, and the universe was filled with nearly equal amounts of matter and antimatter.
But what exactly is antimatter?
It's basically the opposite of matter.
Well, that's a given, but what is it exactly?
Ah, like antiproton, antineutrons, positrons, antineutrinos, uh, photons.
Wait, photons are an antimatter? Aren't they the light things?
Particles.
Particles, yes.
I mean, they aren't matter, that's for sure,
They aren't?
because they have no charge, no resting mass. They're just basically electric fields traveling through space.
Ah, so they're radiation.
Yes,
And that makes them antimatter?
I guess. I mean, I'm not a physicist, so I can't be sure.
Are they called physicists, like the people who study these?
Yes, yes. Correct me if I'm wrong, which I probably am. As I stated earlier, there initially existed an almost equal yet asymmetrical amount of matter and antimatter. These get spontaneously created from protons just as quickly as they find one another and turn back into photons. However, as the universe cools, those matter and antimatter pairs begin to annihilate faster, and it becomes more difficult to find photons that are energetic enough to make them. Fortunately, the asymmetry fell in favor of matter as they were created and decayed without an equal creation or decay of antimatter. As the universe expanded further, common particles began to form. These particles are called baryons, which include photons, neutrinos, electrons, and quarks. This is known as the baryon genesis period, where there were no recognizable heavy particles such as protons or neutrons because of the still intense heat. At this moment, there was only a quark soup.
So the universe felt too hot as a soup and decided to just go boom?
Well, yes, and to be honest, doing research, they say it wasn't a boom. It is more like,
Then why is it called the Big Bang Theory?
I don't know. We can know that for sure. All we know is a Big Bang is an accurate way to describe it.
Weird.
Okay, then, so what would you rather call it?
I don't know, maybe like particle party?
Particle party doesn't sound any better. Eventually, it cools enough that all the exotic particles go away. The antiprotons and antineutrons cancel out with protons and neutrons, leaving out only a small asymmetry of matter over antimatter, bathed in a sea of radiation. Once the universe had cooled to about 3,000 billion degrees Kelvin, protons and neutron particles, known as hardons, became the common state of matter. But no more complex matter could form at this temperature, and after about 1 to 3 minutes had passed, Since the creation of the universe, protons and neutrons begin to react with each other to form deuterium. Deuterium, or heavy hydrogen, is now a signal that light elements can form heavier elements. This process is known as nuclear fusion. Deuterium will then collect another neutron to form tritium, another isotope or hydrogen. These are in essence precursors to what we currently know as hydrogen and helium. By the time this happens, the universe is nearly 4 minutes old and is far too diffuse and cold to undergo the next major step of fusion.
Isn't hydrogen just a proton and an electron?
Yes,
And helium is, if I remember correctly, two neutrons, two protons, and two electrons.
yes, that's right.
Where exactly were these electrons while all of these were happening?
Just know it's too hot for them to react with the hardons and form heavier, more complex elements.
Ah, I see, understood. Essentially, what's stopping them to form anything else? Is it the space they exist in?
Yes, it's either too hot or too cold for certain reactions.
So everything was once just hydrogen or helium nuclei?
Not atoms, but nuclei. After further cooling, excess protons would be able to capture an electron to create common hydrogen. Consequently, the universe today is observed to contain one helium matter antimatter atom for every 10 or 11 atoms of hydrogen. As it turns out, very light nuclei and elements are favored like hydrogen and helium, not only standard hydrogen and helium 4, but also their isotopes deuterium, tritium, and helium 3. This primordial, unprocessed material has actually been detected observationally and is one of the three cornerstones of the Big Bang, along with the Hubble expansion and the cosmic microwave background. And that's where all the elements in the universe started from. Well, you still have to wait tens of millions of years before the universe first starts from.
This is a very, very condensed way of putting what is essentially the start of everything.
Hmm, condensed and mayhaps imprecise telling of it. Everything we are and know, and every material object we've ever interacted with came from this primordial sea of protons and neutrons and was once a mere collection of hydrogen and helium atoms.
So basically, we were all just water particles.
I suppose we were.
This is why we always have to drink water.
Stay hydrated, starlights.
Oh, I like that. Very nice.
The first elements, hydrogen and helium, couldn't form until the universe had cooled down enough to allow their nuclei to capture electrons about 380,000 years after the Big Bang. Less than a second after the Big Bang, the universe was both too hot and too dense for elements to form. Hydrogen didn't appear until the universe had spread out and subsequently cooled, enough for the first protons and neutrons, and later simple atoms to form.
Around 10 to the negative 12 seconds after the Big Bang, neutrinos, quarks, and electrons formed. Protons and neutrons began forming shortly after. Within about 3 minutes after the Big Bang, conditions cooled enough for these protons and neutrons to form hydrogen nuclei, the era of nucleosynthesis. Some of these nuclei combined to form helium as well, though in much smaller quantities. But after 20 minutes, nucleosynthesis ended and no further nuclei could form.